Hi, and welcome to Compositing Fundamentals. This is Learning to See the Art of Observation. Today we can talk about a couple of topics and the exposure triangle, focal length, macro lenses, and artifacts, and everything that a compositor kind of needs to know in order to make shots integrate a lot better and to be able to add those artifacts to our composites to make sure that they look more believable, they look more rich, and we are able to deliver the story in a more believable way. So let's go ahead and move forward and start going through our topics. The first thing that we need to discuss is pretty much camera work. As a compositor, if you have a camera, it's a great idea to go outside and shoot a lot of reference images. But the most important thing about the camera is that we're studying every single image that comes in, and we're trying to evaluate what makes an image believable to the viewer. And that's what we're going to try to mimic in the compositing package when we're doing work inside of Nuke. So the first thing that we encounter is the exposure triangle and the artifacts that this specific area of the camera introduces, right? So the exposure triangle pretty much is composed of three main areas that we're going to discuss in a second that control pretty much if an image is underexposed or overexposed or actually has the perfect exposure that we're looking for. In the left, you could actually see an underexposed image. On the center, you could see a good exposed image, and on the right, you could see an overexposed image. And you could see the artifacts and the look actually and what it looks like when it's actually overexposed, underexposed, or perfect exposure. At the top of those images, you're looking at what we call histograms, and they give us a lot of data, and you probably have seen these inside of Photoshop. It gives us a lot of data about the image and what is really happening with those values. So if you see on the underexposed image, the one on the left, you're going to see that a majority of the colors are towards the left side of the spectrum or the left side of the actual graph. And that what it's telling us is that a lot of values are going to that area that is our black point area. So therefore, the majority of the stuff, like the grass in this case, is a lot darker than it should. So therefore, that's what that histogram is representing. And we don't have a lot of tones on the light areas, like for example the sky. We don't have an overexposed version in there. So you will see that to the right of that same histogram, there's almost no data whatsoever, kind of pushing towards white values. And if you look at the image, there's no white values in that image. Now if you look at the other side of the spectrum, the overexposed image all the way to the right, you're going to see that now the sky is blown out, giving us this no detail whatsoever, but the actual grass looks okay. Now if you see the graph in the top of that image, you will see that the majority of the information is on the white areas or to the right of that graph, so it's pushing to those areas. And you will see that we have very little to no black in that image. So the histogram represents exactly that. Now we see the middle image, and it's a well-exposed image. We have a neutral amount of values, or it has can have a healthy histogram because it has values almost in every part of that area that we could actually tweak or push up or push down. This is extremely important for a compositor because the majority of the times we're working with exposure of images. We're pushing gain up, and gain is pretty much another name for multiply or exposure in this case, right? So we're pushing those values up and down to kind of get the look and the feel of a real image. In the director, to help the story, sometimes he will want us to explode the sky or to overexpose that sky or do what we call an exposure split, right? Where we see in the darks, we see in the lights. It all depends on how a camera really sees. And that's kind of our goal. We're trying to see a composite through the eyes of a camera, not through the eyes of a viewer. So that's essentially what we're trying to mimic in compositing. We're trying to mimic what the camera sees. So moving on, there's these three factors that we talk about in the pyramid, in the exposure pyramid. Pretty much are these three things or these key elements. And the first one is we're going to talk about is the aperture. And the aperture controls the depth of field. And we're going to kind of talk a little bit more about that. But if you see, each of these areas actually introduces a new artifact into the image that we have to mimic in post-production, in this case in compositing. So the aperture, that is the lens area, the mechanical part of the lens, introduces what we call depth of field. Then we got the ISO that introduces what we call grain, and this is kind of the sensor of the camera, and you will see it later on. And then we have the shutter speed that introduces motion blur or blurring into an image. And all those combined give us what we call our perfect exposure. If we balance all those three elements in a camera, it will give us that nice exposure that looks rich. It gives us data in the up areas and in the bottom areas as well as the mid areas. So as a compositor, we're able to tweak those. But understanding what each of these areas are and what type of artifacts it gives us is extremely important to be able to make an excellent composite. So going into the aperture, you could see that it's pretty much the amount of light, right, that enters through that lens. It's like the opening that is actually controlling how much light is coming through the glass into the actual lens, into the actual sensor. Also, it controls the artifact that we call depth of field. And pretty much we call it an artifact, but it's not really an artifact, right? And depth of field pretty much is extremely important because it outlines the areas that are going to be completely in focus and areas that are going to be out of focus. And all these depend on how wide the opening of the lens is versus how small that opening is. Now, everything has a setback because we said aperture is the amount of light that comes through the lens. If we want a good exposure, we need to have some light coming into that lens, right? If we have too much, we overexpose the image. We run that risk. So we need to balance the other two elements in order to get the amount of light correct. If we make it too small, then we don't have enough light, therefore introducing other issues into the image. Now, the other setback that we have with the aperture is the wider the aperture, the wider the opening, the more depth of field we introduce. That means the more areas, the more areas in focus actually are going to be smaller than the areas out of focus. We're going to have a lot more out of focus that goes out of focus quicker versus the area in focus that is going to be a lot smaller. And by the way, depth of field is actually the area of focus, not the area out of focus, okay? So we know it as the area of focus. So it's going to be a lot shallower or shorter. Now, if we close the aperture and make it a small aperture like this one, what we're actually introducing is a lot more sharpness into the image. So we kind of remove the depth of field, so the depth of field becomes longer or wider. Right? In this case, what is going to happen is instead of having the depth of field come in really quickly, right, and with the area of blurriness coming really quickly, it's going to actually be a lot. It's going to take a lot more. So a lot more of the elements that we're trying to keep in focus will be in focus. And the other thing is, this is on your camera, right? It's on the lens. Is the lower the number, actually the wider the aperture is. The higher the number, the smaller the aperture will be. So all those things we're trying to keep in mind. The other cool thing about the aperture is it introduces a couple of other issues, right? Let's go ahead and leave this depth of field kind of explanation so you guys kind of see a little bit more of what is happening. This is me actually changing the aperture so you guys could see. You see that the luminance is not changing more, but the depth of field, right? We're looking at the bokeh effect, that area of blurriness and what it gives us. So if we look at this video, you will see that actually this shape has a specific angles, right? It has specific points in each of these corners, right? And that's the actual intersection of the blades of the aperture. It creates these type of shapes. Sometimes you'll see, depends on the quality of the lens, how many blades it has. Sometimes you will see like a polygonal shape. That means you have 5 blades, and the intersection of those 5 blades creates those issues. Also, based on that, if we move forward, that's one artifact that we need to kind of work out, right? That pretty much is called the circle of confusion. Is the areas where when you have elements in front and behind that depth of field area, it actually, you can't focus too well, right? So the circle of confusion is what we know, those little circles and what is happening on those specific scenarios. I'm trying not to go too much in detail, so it's just like a basic introduction. But the other artifact that we need to mimic, we call an optical artifact as well as an aperture artifact, because it's a combination of glass and the refraction of light plus the actual blades on the lens, is the lens flare, right? The shape of the lens flare, in this case, the actual star shape of that lens flare, is actually dictated by the actual aperture. And again, how many blades does that aperture has, right? And that will dictate those little star shapes that you see, how many points will your lens flare will have on those star shapes. Now, all these other things of the lens flare, all these other artifacts that you see, actually those are created by the glass, right? What we call the optical element of our specific composite in this case, in specific picture, right? In this case, the camera. So all these elements are optical elements. That means is the refraction and reflection and the bounce of the light within the lens components, in this case the glass, going back and forth, and back into the sensor. All right, so later on we're going to take a look a little bit more about those elements, and we're going to show you how to create those in Nuke as well. All right, so that kind of gives us an idea. Now, the next thing that we're going to introduce is the next step on the camera, right? As the image is being captured, it goes through the lens, it goes through the aperture, it creates those initial artifacts that we need to mimic, and then it goes through a mechanical element here that is called a shutter. All right, and the shutter, as you see in this video from Adorama, pretty much is controlling the light duration and motion blur. The longer you keep this aperture open, that means the more light is coming through. Therefore, as an object is moving, it's going to actually seem like it's blurring all the way through. Now, there's another element that controls that light, right? And these are some of the effects that you could do with motion blur. And that's why motion blur is so important for CG work and film work, to make things look smoother, kind of have a little bit more believable factor into it. The next thing is the ISO, or the sensitivity to an image, right? Or sensitivity to light. And the ISO introduces grain and noise in our images. So it's very important that we know what type of grain and noise, and we try to match those based on a film stock or a digital camera. In this case, digital cameras, they don't introduce grain, but they introduce mostly noise. A noise pretty much is based on the pattern that you see in front of you, the pattern of the actual digital camera sensor. The digital camera sensor is composed of many photosites. They are responsible for taking the image that comes from the analog world, in this case is known as the real world, right? That comes through the lens, comes through the shutter, and now is being reflected or bounced into the sensor. So those little photosites, as you see on the illustrations, what they do is they capture that data. And they are arranged in a set of rows and columns, right? So they're very nice and organized. So therefore the noise, when you look at noise from a digital camera, it looks actually more organized than grain. Grain will come from film camera, film stock. It's a chemical process. We got what we call servo highlights. And I would like you guys to research a lot of this stuff, right? And that's part of the process here. We're going to research and troubleshoot and learn about all these things. So the grain is actually coming a little bit more organic. It's not in normal pattern, and actually because it can be controlled. Again, is the little molecules of silver highlight that are on the film emulsion, and those are the ones responsible of getting in the light and bouncing it back and forth. So these are some examples of digital noise, and you could see some of the patterns in there, and you can see some of the straight lines up and down, depends on the photosites. And they're red, green, and blue because the photosites are actually RGB, or red, green, blue. Now, we have talked about all these elements and what type in the exposure triangle, and what type of artifacts they introduce to an image. In this little graph right here, it shows you just a little bit more what does it do to an image when you're shooting at different type of scenarios. Like I said before, a good compositor, usually compositors like photography a lot because they like to go out and kind of understand what is happening in the world around them and how to mimic that in the computer and make everything more believable. So understanding a camera will give you imperative power, right? Incredible power, actually, to be able to make intelligent decisions in the compositing process. So in this case, we could see the shutter speed, we could see the aperture number, and we could see the ISO. And it shows you kind of a little scale, right? If something is more in focus, you will have less depth of field. If something is out of focus, what we call shallow and long depth of field, if something is out of focus and it's short, pretty much you have a little bit wider aperture. The same with the ISO. An image that has less amount of noise, the ISO is lower. More amount of noise, the ISO is higher. That means more sensitive to light versus less sensitive to light. And the shutter speed, the more motion blur we have, pretty much that means we're exposing or leaving that shutter open the longest. And the less motion blur we have, that means we have a shutter that closes in less than a second, right? Quarter of a second or 1/4000th of a second, right? So it's so fast that it freezes motion. So going through lenses and artifacts to kind of finish on the optical part of it, we first have to understand as well the difference between a wide angle lens and a telephoto lens that you probably talk in shading and lighting. And this is a picture I took in Spain, the top one. The bottom one is from the internet, but the top one is a picture that I took in Spain with two different lenses. One I took it with my telephoto lens, and the other one I took it with my wide angle lens. And you can see that the wide angle lens gives us a more broader spectrum of the area that we're actually working on, right? So therefore, this is used for establishing shots and all these other things. So it's very important to us to know these type of lenses and know what they do. You don't have to be an expert at it, but at least understand that if you see this type of images, you know you're working with a wide angle shot. So you have a lot of lens distortion, you have other things, chromatic aberration, there are artifacts that get introduced on the edges. So when we're doing integration, we know what we're looking for. Now, the next one is the telephoto. Is the same location I just put a telephoto lens in there and I shot this image of that statue on the back. Now, you could see how the whole perspective just got flattened, and now I'm a lot closer to that subject. It's less amount of distortion. We have another distortion that we're going to talk about, but pretty much it gets all those objects closer to us. It flattens that perspective. So all these things are extremely important to understand. And this is kind of a difference between a telephoto and a wide angle. You could see more distortion in the wide angle versus a telephoto. Okay? So again, a lot more research that you guys are going to do. The other thing is macro lenses, right? Macro photography, where we have a very shallow depth of field. And this is a great explanation of shallow depth of field, right? These macro lenses, the aperture is a little bit wider, and it actually focuses in a small area, and everything outside of that area starts going into blurriness, in this case defocus, because of these type of properties. So the macro lens is used to make things look small, right? Probably in shading and lighting, you were trying to make a toy look really small, and you couldn't figure out why it wasn't looking quite right. And the reason why is because when you're looking at small things, you have this depth of field right in effect, right? But when you're looking at a nice landscape, usually you don't see depth of field the way that we're accustomed to, right? It's very nice and subtle, right? We have a lot more things in sharpness all the way to the horizon. So these are things that, again, observation is what is going to actually allow you to make these informed decisions and understand exactly what you're looking at. The next thing is chromatic aberration. And chromatic aberration, like it says in the definition, is the failure of a lens to focus all the colors exactly on the same point. And it's because we're using glass, right? And this glass has to be curved in certain ways in order to kind of push the majority of the light through that lens back into the shutter, back into the sensor. So if you look at the left, that's only one single glass, and you could see how the chromatic aberration is getting affected. You see this kind of rainbowish color. And these are things that make an image optically believable, right? Because it doesn't matter how much they try to fix it, you could dictate the quality of the lens actually through the chromatic aberration as well, right? The less chromatic aberration, the more quality the lens is, but you cannot remove it completely. It's always there. That's an optical artifact that happens. So as we move along with this other example, this kind of illustrates a little bit better what a chromatic aberration is, right? Where we see all the lighting rays that are coming from that picture of the moon into the sensor, into the lens, sorry, and they're getting bounced around, and they're trying to get focus back when it hits the sensor, right? So it kind of gives that perfect register. And on the left, you could see that all those rays, without an actual corrective glass, they kind of scatter all around and gives you a blurry image. That is kind of an effect of the chromatic aberration, right? It's a pose artifact as well of the chromatic aberration artifact. So you could see that all the light rays, the RGB, are getting offset, and therefore the image is getting blurrier. Therefore, the quality of your lens, right? The higher the quality, the less of this effect you see, the sharper your image. Now, on the right side, we have a better lens built, right? Where you could see the actual corrective glass or corrective flint in order to be able to kind of focus the rays back into a single point to be able to get a perfect or more closer to perfect type of scenario. And perfect is a really big word because really nothing is perfect in real life. Everything that we do is actually to make our CG images from the perfect render into an imperfect image, and that's our job as compositors, to make it imperfect, because 3D renders actually come out perfect in the sense of mathematics. So moving along, this is another type of fringing. We also is another name for chromatic aberration. You will hear a lot that term, fringing. So when we have this effect of fringing, or chromatic aberration in this case, you could see it on the side here as well with the pens, where out of focus imagery, you could see that chromatic aberration in there. And it's really cool. Directors want to remove it, but a lot of us now are understanding the use of it as an artistic element to kind of give it a little bit more life to an image. On the left side, you could see the actual hawk, and one of the effects of an extremely bright light against a very high contrast or edge, in this case a darker environment in the foreground. What happens here is that the light is so bright that when it hits the sensor, the photosites actually, they're bouncing light back and forth because that's a property of the materials, right? They're kind of bouncing a little bit of light in there. So it creates this type of fringing where you have a very bright light against a very dark element because they're so close together that you get this bounce here. In this case, it's not the lens doing it, it's actually part of the sensor issue in there. All right. So like we said before, a lot of that is gives us blurriness, right? So other things that we need to be looking for as a compositor is the sharpness of an image and the blurriness of an image. When we're actually compositing two images together, we have to evaluate how blurry an image is. So the one that we put on top of that background image, actually we are able to blend it together. If we put an image that is too sharp against an image that is very blurry, then you lose the integration completely. And a lot of people do that mistake because they want to keep all the detail they render. They want to keep all that sharpness. The problem is that the original plate, and plate I mean the background, right, or what we film, is actually not as sharp. So therefore you have to match that level of sharpness. So if it's not as sharp, you have to blur it a little bit. You have to do it. All right. The other type of artifact that we find is lens diffusion. And lens diffusion is this type of glare, this type of glow that in games they call it blooming. So pretty much this is due to the fact you probably have the lens is not clean. It usually happens in cheap lenses. Also happens when the lens is fog. Right? So where you come from a warmer area into a colder, or actually the vice versa, the colder to the warmer, you tend to get this foggy effect. And also there's filters that they sell for that specific dreamlike feel. So we call this lens diffusion. It also happens even if you see a sharp image, you could analyze a little bit the edges of brighter areas against a little bit not so bright areas and then darker tones. And you could see these artifacts that happen, that it creates kind of a glow, kind of a glare that happens around that area just slightly, that gives us that illusion that that area is brighter than its surroundings. The other important thing is contrast. It's extremely important that we pay attention to contrast and how we shoot images or how the images are given to us. If we get an image with too much contrast, and that's kind of an enemy for compositors, one of the issues that we're going to encounter is if the director, for example, in this image, wants us to kind of get more detail on, for example, the ceiling where the lights are attached all the way to the right, top right? There's no detail there. So there's no way of us getting that in because when it was recorded from the camera, it actually was black. So they pushed too much contrast in the camera, so now when we're compositing, we cannot do anything about it. In order for us to fix something like that, we will have to rebuild that area either in CG or use photography in order to build those areas back. So the same thing happens with super whites. If it's a digital camera that doesn't support what we call ranges or latitude, or some people call it high dynamic range, that means above white, there's still values. So above 1, that is white, we still have more values in a film camera, very different than a digital camera. And the director tells us, oh, I want to see the light inside the hotspot area. Let's say on the left side on the top, you see the hotspot there. There's a light in there emitting that illumination, right? So sometimes the director wants to say, oh, I want you to bring that back. The only way that we could do it is if we have the latitude. In this case, the range is above white. A compositor could actually bring them down and we could see the light. The problem is if it's recorded that way and there's no latitude, it's a normal digital camera like a 5D or 7D and something like that, it doesn't have that amount of latitude in there, therefore we won't be able to bring it back. So always we kind of shoot with low contrast images, and then in post-production we do all the color corrections and all the nice looks that we want to go with, but we could push it and we could bring it back. The next thing that lens introduces is lens distortion. We have barrel distortion and pincushion, right? Where for artistic purposes we could actually use it. But lens distortion is a extremely important part of the post-production process. Make sure that we have the proper workflow so we could integrate images correctly. Also for textures, shooting textures and all these other things, it's important that you understand that lens distortion, when you shoot it with a wide angle lens or a fisheye lens or a telephoto, gives you kind of different type of look, so you have to compensate for those. So usually the best way to shoot a texture is actually with a telephoto lens or a lens that actually is a zoom lens, so that way you can stand back further, so there's less amount of lens distortion when you actually zoom in into the texture. So you get an effect that is, if you zoom in too much, you get pincushion, that is the opposite. All right, but it's kind of gives you a better type of scenario. The other thing that a camera introduces is the vignetting effect. And the vignetting effect is very simple. You got a lens that is circular, right? Or spherical, or in this case, round, in nature, and then you have a sensor that is square. So therefore, one of the things that is going to happen is that the amount of light that hits the center of the sensor, in those areas that the actual round edge doesn't include, it's going to get more light, right? And around the edges or the corners, it's going to get less light, giving you this type of nice effect. Now, compositors use vignetting in a creative way. We don't care too much about the vignetting that the camera does, but we care about vignetting for the purpose of focusing the attention to a specific action, specific hero, or something that we need to make sure that the audience looks at. So we use creative vignetting, where we use rotoshapes in order to focus the attention where we need it. So these are important things. Now, to this funny image, right? The importance of studying references. Staying out of bait shouting, "Oh God," doesn't constitute going to church. What we mean by this image, that it's a funny image, is that pretty much the majority of times we all look for references. We have folders and folders and folders for a project that we got to do, and we just leave it there. We never go back and look at those folders, and that's wasted time. That's wasted research time that you need in order to be able to make your shot as believable as possible. The amount of time that you dedicate to your research and the pre-production and the troubleshooting of issues before that you actually encounter them, the faster you're going to be later on, and the better your work will be at the same time. So it's extremely important that you pay close attention to your reference and you study it to the best of your ability. All right? It's not just studying, just looking at it and saying, "Oh, I'm done." No, it's actually studying. It's sitting down, looking at the edges, looking at the edge quality, looking at the blurriness, looking at the exposure, and all these other artifacts that we just talked about. Now, the next section we cover atmospheric perspectives. And this is very important because as a compositor, we need to make sure that we push elements to the back and to the front, so we are able to actually place elements correctly in perspective, in this case, in the atmosphere. Now, what we're going to do is we're going to study a little bit more what happens in the atmosphere. Why the blue of the sky, right? In this case, why the fog look a certain way in a time of day and another time of day. If we look at these two images on the left and the right, and we start evaluating these images, even as a painter, right? In order to be able to create speed paintings of this, is how do I evaluate the color? What is happening here? Well, when we're looking at atmosphere and we're looking at contrast values and level of detail, right? The further the objects recede, right, we lose that what? You could answer it, right? So we lose that detail, we lose that color, so we start getting a less saturated version of that element, and we start losing those values. Now your blacks, what is happening really is that the blacks, that contrast, right, those blacks are actually moving up and getting closer and closer to what your atmosphere color is, or in this case your sky color is. And the very bright values actually stay. So if you had a building all the way to the back over there and the sun was hitting and shining, we will still get that detail of the specular highlight. But the black values will actually start merging and you will start losing that contrast. Therefore, you start losing the detail that you look at. So in this perfect example, you could see the tree detail in the foreground, and as those trees are moving back into space, you could see that you're losing detail over and over and over until you just see silhouettes. So talking about atmospheric perspective, this is you in the world, right? And this is the sun. Now, the most important thing to realize is that you're not the center of the world, right? You're just in a small part of the hemisphere. Either the top or the bottom, it doesn't matter where you are, right? So now that we understand that, when we're looking at the fog and we're looking at haze and how they react to these type of properties, right? The most important thing to understand about fog is that fog is water particles on the air, oxygen molecules, nitrogen on the air, that they actually have, and moisture as well, that they have actually a very peculiar property, right? And the property is, if you have a water molecule on the air, right, they have reflective, refractive properties, as well as specular properties, right? So all those things we got to take into account. So when we look at the haze, is a little bit of moisture in the air, yes, but also you have blocking agents. In this case, pollution, right? You have dust in the air, particles of glass, particles of dirt. And they block majority of the light, therefore creating a very peculiar look, right? So we really understand what is haze and what is fog. In the middle, we can see a combination of both, where we have fog at the top, and then we can see all the way to the infinity almost back there, but we have this lost in contrast, and we have haze on the bottom that actually blocks details that where we're close to, right? Because there's a lot of pollution in there. So when you look at the sky and why the sky is blue, and we try to explain all these concepts, I'm going to go back to an image when we explain this to explain a little bit more after we have seen this. The first thing that we ask ourselves is why we see this grading of the sky, right? Where the horizon looks lighter, and then when we look at the top, it looks darker blue, right? And the first answer is if you look at yourself in the world and you look upwards, right, and you see this darker blue tone in a beautiful blue day or daytime, right? And you have the sun on the top and all this stuff, right, or in the side. What is happening is that you have less amount of distance between you and space, right? And space is dark, it's black. Therefore, you get that combined with the blue that you're getting from the sky, and therefore you got a darker tone of blue, right? But the first thing is, as you're going to the atmosphere, right, and as you're looking down, back down, and you look at the horizon, it starts getting lighter and lighter and lighter in tone. And what is happening? Well, you have a lot more molecules of water, and then if it's haze, it will be dust. But if it's moisture in the air, and all these things are blocking that element and are absorbing and bouncing light all around and creating specular highlights that actually generate a lighter tone, all right, because there's more substance between you and that horizon. Now, the most important thing to do is if we go back here and we start kind of explaining a little bit more what this image is right here, let's kind of analyze it a little bit more, right? If we look at the area on the right side, we're looking at the right side image of the mountains, right? And we see this kind of blue, kind of hazy, but in this case it's more foggier scenario, right? We have a lot of plant life, so therefore we're going to have a lot more moisture in the air. Therefore we got more fog in this case, right? As elements recede in space, we already talked a little bit about that. But let's talk about the colors, right? If you look on the shadow, it looks bluer. But if you look on the light areas, right, like to the left, on the mountain on the left in front of you, it looks kind of warmer. And it has this color that is mixing with the background, right, as well as a little bit of blue. So what we want to do is explain a little bit what is happening here. If this is fog, right, and we're working with fog in this scenario, right, we are in nature right now. What is happening is all these water molecules in the air, because they have reflective, refractive properties and specular properties, right? What they're doing is when they're in the shadow, they're not getting any specularity from the sun. Therefore, you don't see a very bright light or a very bright scenario in the shadow area. But they're actually bouncing and reflecting and refracting the sky around it. And the sky actually has this blue tone. So that blue tone gets absorbed by these molecules and combined with the background, and you get this type of dark, nice shadow, right, that has this bluer type of feel. Depends on the blue of the sky. It's because of the reflective and refractive properties. Now, when those water molecules are actually on the sunny side, where they actually not blocked by the shadow of the mountain, now they actually have the blue of the sky, the reflection and refraction of the background. That's why we lose detail as it goes back, right? It's refracting, so it's distorting that background. But now that those molecules are now in the sunny side, they now added, on top of that, you added the specularity, giving you that brightness value that you see. And that's why sometimes you see that it explodes a little bit more. The exposure is higher in those areas. But now you can see all the details. Nothing gets merged anymore because we can see through that lighting, as well as combine it with the color on the back. So there's a lot of reasons, right? Very interesting reasons. Now let's talk a little bit more about the sunset and the sunrise, right? So, in order to talk a little bit more why the sky is blue, the first thing we have to introduce is the light rays, right? So, the sun is actually white. A lot of people think that the sun is yellow. Well, the sun is 0.0000, and you could put a thousands of O in there, I don't know, more, zero point 0.1 yellow, okay? The thing is that it's so hot that the hotness value actually, when we look at it with the naked eye, will be completely white. Right? But if you look at it through a telescope that has filters on it to lower that intensity, yeah, you will see this warm kind of chunk of star, right? But pretty much to the naked eye, the sun is completely white. So if you go to space, it will be white. But my question, a lot of people ask actually, and the question of a lot of students is, but why it seems warmer when we look at it through our eyes here in the Earth? And the answer is very simple. you have a lot of atmosphere between you and that object. And what happens is, if you look at this graph, the white light is composed of all these colors of the spectrum. On the visible light, in this case, we're talking to, because also we have the visible parts of the spectrums that we can't see, like X-rays and all these other things, right? But this visible light spectrum, and we have red, green, blue, right? So what happens when we got the white sun sending all this white light into the earth, right? All those rays, and we have the atmosphere right in the middle, right? We will have a process that is called absorption, right? And scattering and radiation. So in this case, what happens is all those rays come through the atmosphere, and the atmosphere has all this oxygen, nitrogen molecules on the air, right? And moisture on the air. So what they do is they actually take the light rays and they start absorbing different type of light rays. So in this case, the red is actually faster. The red spectrum is actually faster than the blue spectrum, or the cooler colors. So what happens is that the blue light rays, or the blue light spectrum, actually gets absorbed a lot quicker by all these molecules, and then they get scattered after that effect, versus the warmer tones, in this case the red, the oranges, the yellows, they actually, because they're a lot faster, they don't get absorbed by these. Some of it does, but it doesn't get completely absorbed by these molecules, so therefore it goes to your eyes straight through. And that's why we see the orange color of the sun. That's why we see this warmer tone. It's because those red light rays are actually hitting us a lot quicker than the blue light rays, so the blues are getting scattered. Now that we know this, pretty much it's very simple to understand a little bit more of the sunset. When we look at a sunset, the sun is so far away from us that what is happening now is that the majority of the blue rays are getting completely absorbed, almost entirely absorbed by the actual atmosphere. And then the red tones, because they're more faster, right? They're actually reaching our eyes a lot quicker. So therefore they could travel longer distances that the blue tones can't. Now, if you go ahead and watch your sunset, right, some of you will see a little bit of kind of this water turquoise color in a gradation, and it goes into a purple at the top, and then you see these nice oranges and yellows at the bottom. And again, you have to realize that still is a hemisphere, so that curvature, some of the rays will actually hit the top closer where you are, and you still get some blues in there mixed with the yellows to give you this greenish turquoise watercolor. All right, so you still have some of that happening and all around. So the sunsets are very beautiful to watch and kind of see and understand them as well. So there's a lot of reasons here, and why the skies are, the clouds, people ask why the clouds are mainly white, is because after part of that rays are getting absorbed, still the clouds always have a warmer tone to them, but after all those rays are getting absorbed, right, still some blue comes through, and the rest of the light spectrums are coming through. So clouds are pretty much water. It's pretty much water molecules on the air. In this case, compacted a little bit better. Again, scientifically, I'm not a scientist, but it's kind of a little bit better like that, right? It's cloud droplets pretty much. So what they do is they are not absorbing any light. They're just transferring that light through, and because they're transferring almost 100% of those rays back into the viewer, we tend to see white. Again, the combination of red, green, and blue in equal amounts equals white. So therefore, if you're bouncing back all the rays back out, or the majority of the rays back out, depends on depth, pretty much you're seeing white. And that's essentially what happens there. So now that we have understood this, and now that we understand based on distance, based on where we are in a hemisphere, how haze and fog work, that's essentially is going to help you understand how you need to push an element back when you're integrating it into a blue sunny day, or you're integrating it into a nice sunset. You will understand what type of value, what type of color, and how much contrast do I need to push that element to in order to be able to make it look like it's really far away. So this will help you as a compositor and as an artist as well, because when we're painting, for example, doing speed paintings and all these things, we actually think about all these elements when we're putting colors. So these are some examples of real life scenarios, and you could see on the top left the sunset look that I was telling you about. You can see this nice oranges and purples, but the top area you still see the blue, right? And it's because the rays are actually traveling through space and hitting that top section of the hemisphere. So that's why you still see those blues. The lower the sun is on the horizon, you start losing some of those blues and start getting more warmer tones. And the same idea. We could see haze on the right hand side of that image. Okay, how the light travels through the haze, and you can see that is blocking a lot of the details. So there's a certain point that haze starts pretty much occluding everything else, and we can't see even the shapes. And on the top here, we could see that a picture over the normal skies, over the clouds, and you could see at the top very dark valleys, right, of blues, and you could see the horizon very light values. And on the right side of that, we could see a normal day where you got your white sky, your white clouds, and your beautiful blue sky. Okay, so other topics of interest that I would like you guys to kind of research a little bit more and start working with, as well as you're going to be reading a little bit more of the book as well, is these topics, right? Chip charts, exposure and dynamic range, underexposed, overexposed, that we already talked about, but I want you guys to really, really dive into that. And HDRI, or high dynamic range, that we talk a little bit about it. We call it latitude in film cameras. And camera artifacts and integration into games. Extremely important that you kind of look at that. Moving along here, I will show you a little bit of that. I think one of these has a video that is pretty intense in the sense, is from Crysis. But calibration charts, how we use these, I want you to research that. High dynamic range images, how we use it to achieve today's workflows and visual effects. And this will be part of your first discussion. And this is Crysis, sorry, I scare you. But you will see chromatic aberration on this. You will see a lot of other stuff in here, right? Sorry for the scare on that, but it will kind of wake you up, right? Motion blur. All right, we have the lens diffusion that we talked about, depth of field in games. Beautiful, beautiful atmospheric perspective. Again, this is Crysis Engine 2. This is really old, but still, it looks amazing, amazingly good. And this is all in games. Chromatic aberrations, Ace Combat, and how that is used in map paintings in order to make map paintings look believable. This is from Matte World Digital. All right, and this is how pretty much the integration. You can see all the light, you can see the sky, you can see the clouds, how all that is integrated, the atmospheric perspective, how all that makes this look believable, plus all the moving elements that make an image, a map painting in this case, look completely alive. So these are a lot of beautiful things, beautiful scenarios that we will encounter through our process, right? A lot of game stuff, a lot of film stuff. So that's pretty much being it for today's lecture, and I hope you enjoyed it. Again, this has been The Art of Observation, learning to see, and look forward to seeing your work. All right, this is Pedro Flores. Take care. Bye-bye.